So here we're going to look at some wave basics, things that we need to know before we can go much further in the topic. So waves are all around us. Think of light. Light can be is considered a wave. Waves on a rope, waves in on a pond, ripples, waves in the sea, microwaves, infrared waves, such electromagnetic waves, which we'll look at later in the topic. So waves are all around us and are a fundamental part of physics. So let's imagine that you are causing vibrations or oscillations on a rope. Okay, so nice and simple to start with. And if you were to leave the rope with putting no energy in to not cause it to vibrate at all, it would just lay flat like so, this red line here. And that's what we would call our equilibrium position or rest position. So equilibrium position. So that means that the rope would go back to rest there, or if there was no vibration. So the larger the vibration, that means there's a larger displacement and there's a larger distance from this equilibrium position. Okay, and this is what leads to what is called our amplitude. So I'm going to label that A, our amplitude there. So amplitude is our maximum distance from the equilibrium position, our maximum displacement. And you can see that's led to the top of this wave. And we call these tops of these waves peaks or crests. Think of crest of a mountain or peak of a mountain. That's the top of the waves. But you could have just as likely labelled the bottom here. And if I had drawn this properly, these two distances should be the same. So that's our amplitude there as well. Okay, but now that would be called our crest, our trough. So think of it like a horse's trough. It put its head into the trough, okay? So these two distances would be the same, and that's amplitude. Amplitude, the unit of amplitude is usually in meters, okay? Amplitude, maximum displacement. Common mistake is people try and label it from peak to trough. They label here as amplitude. That's not correct. It's from this equilibrium position. Another important one is our wavelength. Now, us physicists are lazy. We don't like using lots of words. So we're going to use a symbol instead for wavelength, and this symbol is lambda. Okay, so that's the symbol for wavelength. So a wavelength is just the distance of one complete wave. The distance of one complete wave. So there, it's peak to peak, okay? Or we could also label here from trough to trough. That would be one wavelength as well. We could also go from the equilibrium position. So here it's gone up and then come back down to where it started. So that would be one wavelength as well. Anywhere where the wave gets back to where you've started it from, that is one wavelength, the distance of one complete wave. Other things we need to know is the frequency. So the frequency is, think of the word frequent. Frequency means how often something happens. If you go to the gym frequently, you go a lot of times. So frequency is all about how many waves pass a point per second. Number of times a wave passes a point per second. So instead of saying per second, we use a unit, hertz. So hertz just means per second. So 50 hertz would just mean 50 waves per second. 10 hertz, 10 waves per second, and so on. So frequency, number of waves per second. So if you had a high frequency wave, the wavelength may be smaller because they're closer together. Lots of waves passing a point in a short period of time. If you have a low frequency, not many waves passing a point per second. If we had a very high amplitude and a very high frequency, we make something like that, high frequency and high amplitude. So what else do we need to know? The other thing is time period. Time period just refers to the length of time, usually in seconds, for one complete wave to pass. So how long does it take for one wave to pass? So the time period, we can work it out, is just 1 over the frequency. So let's say the frequency was 10 hertz. That would mean the time period would be 1 over 10, which would give us 0.1 seconds for one wave. So that means each wave takes 0.1 seconds to pass a point. Well, that would make sense, isn't it? Because if it's 10 hertz, that means there's 10 waves per second. So 10 times 0.1 gives you 1. So let's look at what we need to, let's look at some examples. If you are standing in a wave pool and 30 waves pass you in 1.5 minutes, what is its frequency? So 1.5 minutes, it's not that much use in minutes. We want to convert that straight away. So 1.5 minutes would be 90 seconds, wouldn't it? What is the frequency? Well, there's 30 waves. So frequency was number of waves per second. So we've got 30 waves over a time of 90 seconds. We've got 30 over 90, 3 divided by 9. So it's about 0.3, if we round up, 0.34 hertz. Don't forget our unit, okay? And that makes sense, doesn't it? That means that you're not getting a full wave per second because there's only 30 waves passing you in 90 seconds. So it's taking more than 1 second for a wave to pass, isn't it? What is the wavelength? So let's look here. If we've got these set of waves here, how would we work out the wavelength? Well, we've got a label of 36 meters, but it hasn't given us to it at a point of a peak to a peak, so we have to figure it out. So when you count how many complete waves there are for wavelength, wavelength is the distance of one complete wave. So we can go, well, if we could start from here, that's 1, 2, 3, 4, 5, and 6. So there's 6 waves in 36 meters. That would give us each wavelength is 6 meters. What about this one? So this time starting on a peak, so we're going 1, 2, 3.5, so 3.5 waves. That's 3.5 waves in, let's say that was 7 meters rather than 7.5 to make it easier. So we've got 7 meters and we've got 3.5 waves there. So what would the wavelength be? Let's think about it. 3.5 waves in 7 meters. Each one must be 2 meters long. That will then give us 7. 3.5 times 2 gives 7. Right, let's think about what waves transfer. So let's go back to thinking of that rope on the string. But let's, instead of having lots of waves per second, like that, lots of waves being passed on the rope, lots of oscillations, let's think that you maybe just send one wave down on a rope, okay? So, and let's say you tied a ribbon onto the rope. So let's say you tied that ribbon there, okay? Now you're sending that wave, you're oscillating that wave down the rope, you're just sending a quick flick down the rope. Well, where's this wave going to go to next? Well, this bit of the wave's going to come down, and the wave's going to move on to over here. Well, where's that ribbon? That ribbon is still tied on to that part of the rope over there, isn't it? So the wave has moved, the wave has moved this way, isn't it? The wave has transferred, and you've also transferred energy over here, haven't you? Because you're moving energy over here. But what's stuck over here? The ribbon's stuck. So the matter is stuck. The matter is not transferred. So what do waves transfer? They transfer energy, but they do not transfer matter. And that is the same for all types of waves. Okay, so if you're light waves, microwaves, sound waves. So if we think of sound waves, some people think that, oh, if you're speaking, that means that the vibrations of the air is moving towards you. That's not right. It's the vibrations are moving towards you. So in sound is just vibrations of air. So these air particles moving back and forth here, and energy is being transferred along, and they're like bumping into each other, almost kind of more like dominoes. But the air particles themselves are then returning to their equilibrium position, just like our rope did. So the air particles are not moving, just the energy is moving. So waves transfer energy, they do not transfer matter. Matter is not transferred. That's very important. Even water waves. So now, yes, it is true that water waves, if something is near the shore, in the sea, that something would be pushed towards the sea. But that, it gets a bit complicated because of the interaction with the shore when you're near the beach. But if we think of water waves deep out at sea, well, it still works there that waves do not transfer matter. They just transfer energy. And think about it. That's why you get these massive things of plastic, these big islands of plastic in the middle of the ocean, because the matter is not transferring. The water particles are moving back to their equilibrium position. It's only when you're near the shore that things are messing about with the wave, the shoreline, that it doesn't hold. So all waves transfer energy. They do not transfer matter. In the same way that we talked about up here, that frequency can be changed of a wave. Think about it. You're changing the speed that you're vibrating the rope. You're changing the frequency, or changing the frequency of sound. Well, that means you could be transferring information. Think about Morse code, isn't it? That's just you controlling a sound, a frequency of a sound. We can do it also with light and radio waves as we transfer information. So waves transfer energy, and they also transfer information, but they do not transfer matter. What else do we need to know for some basics? We need to know types of waves. So there are two main types of waves that you need to know. Two different types of classification. First thing we need to know about is whether they are mechanical, or EM, which means electromagnetic. So I'm not going to go into a lot of detail what we mean by electromagnetic waves at this point. We'll do that in another video. But electromagnetic waves are radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma rays. So electromagnetic waves do not need matter to travel through. Okay, so electromagnetic waves can travel through vacuums, and they can travel through space. Okay, so light is an electromagnetic wave. Light can travel through space from the sun to Earth, can't it? Mechanical waves do need matter. So sound would be a mechanical wave, wouldn't it? Sound is the vibration of air, or the vibration of a solid. If you put your ear on the table and you tap the table. In that film Alien from the 1980s or whatever, when they say in space no one can hear you scream because there's no sound in space, because there's no air, it's a vacuum. So mechanical waves do need matter. So sound uses air, rope, water waves is all using matter, earthquake waves are all using matter. So that's one type of classification. The other thing we need to know is about transverse and longitudinal waves. So this is the classic physicist experiment where your teacher pulls out a slinky, a spring, and you get to play around with it as a class. So longitudinal waves, that would be the slinky doing what, transverse waves, the slinky would be doing what we just talked about there, would be going, and it would look like the slinky's moving side to side. So if the wave is being transferred this way, the vibrations are moving side to side to the way that it's transferring. Now we don't say side to side, however, okay, so the wave's going like this, and the vibrations going side to side. But instead of saying side to side, what we're going to say is our official definition we need to absolutely learn for this, comes up nigh on every single year. Transverse waves are when the vibrations, these vibrations here, are, think of this, they're perpendicular, aren't they? They're perpendicular to the direction the wave is traveling. The wave traveling that way, the vibrations are perpendicular to it. If the wave was traveling up this way, they'd still be perpendicular to it like that. So they're perpendicular to the way the wave is traveling, or the way the wave's energy is transferred. Longitudinal waves, that's when, if the wave's transferring that way, that would be like pulling the slinky back and forth. So the vibrations would be like this. Okay, so instead of saying back and forth, well, now think about these directions, that's parallel, isn't it? So longitudinal waves are when the vibrations are parallel to the direction the wave is traveling, or the direction the energy is being transferred. If you were holding it over here, and the teacher was sending the vibrations down to you, you would feel the energy over here, wouldn't you? So the energy is being transferred to you over here. The waves traveling towards you, but the vibrations are parallel. Okay, so transverse vibrations are perpendicular to the direction the wave is traveling. Longitudinal, the vibrations are parallel. You need to know some examples of these. So longitudinal would be sound is a longitudinal wave. Okay, and there would also be some types of seismic waves as well, so some types of earthquake waves. What about transverse? Transverse would be all of our electromagnetic waves that we'll cover in a later video, all of them, light and infrared, etc. Think of also ripples on water would be transverse. Think of ripples, if you looked at them sideways, you'd see it vibrating, and that's because it's perpendicular to the direction the energy is traveling. Think of the rope that we just looked at over here at the start, that would also be transverse as well. So those are different types of waves, and those are an absolute must. Those definitions are an absolute must that you must learn them.